The entire surface of the world's ocean just reached the hottest temperature ever recorded, and it happened in the 1 month of the year when that should be impossible. On the 22nd of August, the global sea hit 21.1 degrees Celsius, beating a record that had stood since March of 2024. But records set in March make sense, because that is when the ocean is warmest. This one came in late August, when the sea is supposed to be cooling down. The heat is pouring out of the Pacific, from a force that has been building for months and has not even reached full strength. Scientists have been dreading the line the ocean just crossed, and tonight you will understand exactly why. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment and tell me where you're watching from tonight. Let's get into it. Part 1. The Record. Nobody was watching for. On the 22nd of August, 2026, the surface of the world's ocean reached an average temperature of 21.1 degrees Celsius. That single number, pulled from the monitoring systems of the European Union's Copernicus Climate Change Service, is the warmest the global sea surface has ever been measured in the entire instrumental record. Not the warmest for a summer, not the warmest for the Northern Hemisphere. The warmest, full stop, across every day that human beings have had the tools to measure the whole ocean at once. Now, a number like 21.1 degrees does not sound frightening on its own. If I told you the water at a beach was 21 degrees, you would call it pleasant, maybe a little cool. But that is not what this figure is. This is not the temperature of one beach, or one sea, or one current. This is the average temperature of the surface of every ocean on the planet at the same moment. A single value that stands in for an area so large it covers most of the world. And when you are averaging something that vast, moving the number even a little takes an almost unimaginable amount of heat. The ocean does not tick upward the way a thermometer in your kitchen does. To lift the global average, you have to add energy to a body of water that wraps around the entire Earth. So the story here is not the 21.1 by itself. The story is that this number just went higher than it has ever gone, and the moment it happened is all wrong. Here is the part that made scientists stop and look twice. The previous record, the one this reading just beat, was 21.09 degrees Celsius, and it was set back in March of 2024. The margin between the old record and the new one is tiny, barely 1/100th of a degree. On paper, that looks like almost nothing. But look at the calendar. The old record came in March. This new one came in late August. And those 2 months could not be more different when it comes to how warm the ocean is supposed to be. I will come back to why that timing matters so much, because it is the thread that runs through this entire story. For now, just hold on to the strangeness of it. The ocean broke its all-time heat record in a month when, by every rule we understand, it should have been cooling down. There is one more detail worth sitting with before we go further. This was not a one-day fluke, a single strange reading that popped up and vanished. The same value, 21.1 degrees, was recorded on the 21st of August, and again on the 22nd. 2 days in a row, the global ocean surface sat at the very top of the chart. A single record day can sometimes be explained away as noise, a wobble in the data. 2 days holding the highest number ever measured is not noise, it is a plateau. The ocean climbed to a place it had never been and then stayed there. It also helps to know how the global sea surface number is put together day after day, because the machinery behind it is part of what makes a new record credible. The Copernicus service does not wait for a single perfect measurement. It ingests a constant stream of observations from around the world, satellites reading the ocean from orbit, instruments on buoys and ships and floats, and it folds all of that into a physically consistent daily estimate of the sea surface. That estimate is produced the same way every day, by the same system, so a record is not the product of a new method or a changed instrument. It is the same yardstick that produced yesterday's number and last year's number, now reading higher than it ever has. When a measurement system that's steady posts a new high and then repeats it the next day, the record is not an artifact of how it was measured. It is the ocean, and the institution reporting it has no incentive to overstate the case, which matters when a number carries this much weight. Copernicus is a monitoring service, not an advocacy group. Its job is to report what the instruments show, month after month, whether the news is dramatic or dull. Most days the number it publishes passes without comment. It is only when the ocean does something it has never done before that the report becomes news, and even then the language is careful and measured. So when the service flags a record and its climate lead describes an ocean under growing stress, that is not a search for attention. It is the restrained verdict of the people whose entire purpose is to watch this number and describe it accurately. The person who put words to it works at the European Centre for Medium-Range Weather Forecasts, the institution behind the Copernicus Climate Service. Her name is Samantha Burgess, and she is their strategic lead for climate. When the record came in, she said it was, in her words, another clear signal of an ocean under growing stress. And then she added the part that matters most. El Nino, she said, is adding heat to the system, but it is doing so on top of decades of human-driven warming. Read that again slowly, because she just handed us the whole shape of the story in 2 sentences. There are 2 forces here, not one. There is something happening in the Pacific right now, a natural event called El Nino that is dumping heat into the system, and underneath it, there is a slower, heavier thing that has been building for decades. The record we just saw is what happens when you stack the fast thing on top of the slow thing. Let me put the 2 record dates side by side because the contrast is the entire point. The old record, 21.09 degrees, landed in March of 2024. That was during a previous El Nino, and it came at the natural high point of the ocean's year, the springtime peak when the global average is supposed to be at its warmest. In other words, the last record was set with the calendar helping it. It happened at the moment of the year most likely to produce a record, riding the top of the seasonal wave. This new record had no such help. It arrived in the back half of August, months after the yearly peak, at a time when the ocean should be shedding heat, not gaining it. Same planet, same measurement, 2 records barely 1/100th of a degree apart, and yet one was handed every advantage by the seasons, while the other fought the calendar and won anyway. And notice what the margin itself is telling us. 1/100th of a degree sounds like a rounding error, and if this were a single instrument reading in a single place, it might be. But this is a global average built from satellites, buoys, ships, and floats, cross-checked and reconstructed, and the people who maintain it do not casually announce a new record for noise. When a figure that steady, that heavily averaged, ticks past its previous high and then holds there for a second day, it is not the measurement wobbling. It is the ocean actually being warmer than it has ever been recorded. The smallness of the margin is not reassurance. It is the leading edge of a line being crossed, the first day the number went somewhere it had never gone. There is also a reason this specific institution is the one making the call. Copernicus is the European Union's climate monitoring service, and it is not a fringe operation or a single research group with a point to prove. It runs one of the most closely watched climate datasets on the planet, the same system that issues the monthly bulletins the world's press reports on when a month turns out to be the hottest on record. When their strategic climate lead stands up and describes the ocean as being under growing stress, that is not activist language. That is the measured verdict of the people whose entire job is to watch this number and get it right. That is where we're going over the course of this. We're going to take that number apart. We're going to look at what 21.1 degrees actually means, why a late August record is so deeply unusual, and what is happening in the Pacific Ocean right now that pushed the whole planet's water over a line it had never crossed. Because the title of this is not an exaggeration, and by the end you will understand exactly why. The Pacific just crossed a line, and it is a line that people who study the ocean for a living have been quietly dreading for years. And the most unsettling piece of all is this: the thing driving the record has not even peaked yet. Part 2. What 21.1 degrees actually is. Before we can understand why this record is frightening, we have to understand what it is measuring, because a global sea surface temperature is a strange and enormous kind of number, and most people have never had a reason to think about how it is built. Start with the surface itself. When scientists talk about sea surface temperature, they are talking about the temperature of the top layer of the ocean, roughly the uppermost few meters of water. This is the skin of the ocean, the part that touches the atmosphere, the part that trades heat and moisture with the air above it. It is also the part that drives our weather. The warmth in that top layer is the fuel that feeds storms, the engine that pumps water vapor into the sky, the surface that hurricanes reach down and draw their power from. So when we measure the temperature of the ocean's skin, we are not measuring some abstract scientific curiosity. We are measuring the size of the tank that the planet's weather runs on. Now make it global. The figure of 21.1 degrees is not taken from one spot. It is an area-weighted average of the sea surface temperature across the world's oceans, stitched together from an enormous web of measurements. Satellites pass overhead and read the infrared glow of the water. Buoys bob in place and radio back what they feel. Ships log the temperature of the water they sail through. And beneath the surface, a fleet of robotic floats called the Argo Array drifts through the sea, rising and sinking, sampling the water column and beaming the data up. All of that gets pulled together, checked against itself, and blended into a single consistent estimate of what the whole ocean surface is doing. That blended, physically grounded reconstruction is where the 21.1 comes from. There is a specific word buried in the headlines about this record, and it is worth pausing on. The record is described as the highest non-polar sea surface temperature. Non-polar. That means this average deliberately leaves out the ice-covered seas at the very top and bottom of the world. The reason is practical. Near the poles, sea ice and the freezing point of seawater distort the picture, so the global surface figure focuses on the vast band of ocean between roughly 60 degrees south and 60 degrees north. And here is what that actually captures. It captures nearly all of the tropics. It captures the entire span of the Pacific, the Atlantic, and the Indian Oceans across their widest, warmest stretches. It captures the part of the planet where most of the sun's energy lands on water. In other words, the non-polar ocean is not some trimmed-down slice. It is the great warm heart of the world's water, the part that matters most for heat, for weather, and for life. So now think about what it takes to move that number. When you average the temperature across a surface that enormous, a single warm patch, even a large one, barely registers. A marine heat wave off one coastline might raise the water there by several degrees, and it would still be nearly invisible in the global figure because it is being diluted across the entire planet's ocean. For the global average to climb by even 1/10 of a degree, warmth cannot be confined to one region. It has to be widespread. The heat has to be showing up nearly everywhere at once. This is the fact that reframes the whole record. Water has an extraordinary capacity to absorb heat. It is one of the most heat-hungry substances in the natural world, which is exactly why coastal climates are milder than inland ones, and why it takes forever for a pot of water to come to a boil. To raise the temperature of a thin layer of water is one thing. To raise the average temperature of the top layer of every ocean on Earth is something on a scale that is genuinely hard to hold in your head. The energy involved is not measured in the units we use for weather. It is measured in quantities that belong to the physics of the whole planet, and that is the quiet horror hiding inside a gentle-sounding number. 21.1 degrees is not warm in the way a bath is warm. It is warm in the way that only happens when a truly staggering amount of extra energy has been loaded into the ocean and spread across its entire surface. The number is small, what it represents is not. Here is a way to feel it. The ocean holds the overwhelming majority of the extra heat that has been trapped on Earth in recent decades, the vast bulk of it, far more than the atmosphere or the land or the ice. The sea has been quietly absorbing that heat, acting like an enormous buffer, taking the energy in and hiding most of it below the surface, where we do not feel it day to day. The sea surface temperature is the one place where that hidden heat becomes visible. It is the ocean's face, and when the face reaches a temperature it has never reached before, it is telling you something about the enormous body of water behind it. To grasp how much energy is hiding in that hidden buffer, it helps to compare water to air. Water can hold enormously more heat than the atmosphere can, several thousand times more per unit of volume. That is why the ocean, not the sky, is where nearly all of the planet's trapped extra heat has gone. The atmosphere gets the headlines because we live in it and feel it, but the atmosphere is a lightweight. It warms fast and it cools fast. The ocean is the heavyweight. It takes heat in slowly, hoards it, and gives it back slowly, and because of that it sets the long-term terms for the entire climate. When you warm the ocean, you are not adjusting the weather for a week, you are moving the thing that the weather is built on. That is also why the surface reading is only the visible tip of the situation. Most of the extra heat the ocean has absorbed does not stay at the surface. It gets mixed downward, carried into deeper layers by currents and turbulence, stored hundreds of meters below where no satellite can see it, and no swimmer will ever feel it. Scientists track this separately as ocean heat content, and it has been climbing relentlessly. So the surface temperature we're talking about is not the whole story of the ocean's heat. It is the part that has surfaced. It is the fraction that has risen high enough and spread wide enough to show up on the ocean's skin. Behind that 21.1 degree face is a body of water carrying far more stored energy than the number alone reveals, and the surface is where that stored heat does its work on us. The top layer is the handoff point between sea and sky. It is where evaporation loads the atmosphere with water vapor, which is both the raw material for rain and itself a heat-trapping gas. It is where a hurricane passing overhead reaches down and pulls up the warmth it needs to intensify. A warmer surface means a bigger fuel tank for every storm that crosses it, a moister atmosphere above it, and a greater capacity to move heat and water around the planet in ways that end up as weather over land. So this number is not a marine curiosity that stays out at sea. It is the size of the engine that drives a large part of what the sky does to the places people live. So when you hear 21.1 degrees, do not picture a warm afternoon at the shore. Picture the entire surface of the world's ocean, from the equator out toward both hemispheres, running hotter, on average, than it has at any point we have been able to measure. That is the real size of this number, and the next question is the one that turns a record into an alarm. Why did it happen now, in the 1 month of the year when it should have been impossible? Part 3. Why August is the wrong month. To understand why a record in late August is so strange, you have to understand that the global ocean has a rhythm, a yearly breathing pattern, and that pattern is not the one most people would guess. If I asked you when the world's ocean is at its warmest, your instinct would probably be to say the height of summer, and you would be right, but you would be thinking of the wrong summer. The global sea surface does not peak in July and August. It peaks, on average, in March and April. That feels backward until you remember a simple fact of geography. Most of the planet's ocean is in the southern hemisphere. The south is where the water is, and when it is March, the southern hemisphere is coming out of its summer. So the global ocean, weighted by where the water actually is, reaches its warmest point in the early months of the year, following the southern summer, and then it slides downhill from there. That means by late August, the global ocean average is normally on its way down. It has passed its yearly peak months earlier, and it is settling toward the cooler part of its cycle. August is supposed to be a month when the number is falling. The ocean, in its ordinary rhythm, should be exhaling right now, letting go of heat, drifting back down its seasonal slope. Instead, it just set an all-time record. Sit with what that requires. For the ocean to hit its highest value ever in a month when it should be cooling, it does not just have to be a little warm. It has to be so far above its own normal seasonal line that it overshoots the springtime peak from 5 months earlier. It has to be running hot enough right now, in the downhill part of its year, to beat the number it set at the very top of its uphill climb back in March of 2024. Think of it like a runner who posts their fastest time of the day, not at the start when they are fresh, but near the end when they should be exhausted and slowing. When that happens, you do not shrug. You ask what is pushing them. Think about what the ocean has to do, physically, to pull this off, because it clarifies why the timing alone is an alarm. In late August, the sun has already moved on from the southern hemisphere, where most of the world's ocean sits, and that hemisphere is deep in its winter. The natural flow of energy at this time of year is out of the Southern Ocean, not into it. The global sea surface should be losing heat on balance, drifting down its seasonal slope the way it does every single year. For the ocean to instead be setting an all-time record, it has to be gaining, or at least holding, heat at a moment when the planet's own geometry is trying to take heat away from it. Something is not merely adding warmth. It is adding warmth faster than the season can remove it. That is a different and more serious claim than simply saying the ocean is hot. Plenty of individual regions run hot in any given month. What we are describing is the entire global surface overriding its own strongest seasonal tendency, at the scale of the whole planet, at the exact time of year when that tendency should dominate. It is the difference between a warm spell and a system that has been pushed hard enough to ignore the calendar, and the only forces large enough to push the whole global ocean that way are the ones we have been building toward. A Pacific event of rare strength and a baseline of accumulated heat that has raised the starting point for everything. And there is a way to measure exactly how far off the normal line the ocean has drifted, because scientists do not just track the raw temperature, they track the anomaly, the gap between where the temperature actually is and where it normally would be for that specific day of the year. To build that normal, they use a long-term reference period, the years from 1991 to 2020, and they average what the ocean did on each calendar day across all of those years. That gives you the expected value for, say, the 22nd of August. Then you compare today against it. On the 21st and 22nd of August 2026, the global ocean surface was running about 0.67 degrees Celsius above that 1991 to 2020 average. And here is the detail that should make you lean in. That gap, 0.67 degrees above normal, was the widest such gap recorded at any point in all of 2026 up to that moment. Not just a large departure, the largest departure of the entire year. Let me untangle why that stacking of facts matters, because it is easy to let it slide past. The reference period they are measuring against, 1991 to 2020, is not some cool, pristine, pre-industrial baseline. Those 3 decades are already warm. They already contain a great deal of the warming that has reshaped the ocean. So when today's ocean is running 0.67 degrees above that already elevated baseline, the departure is not being measured against a cold old world. It is being measured against a recent warm world, and it is still standing far above it. The bar was already raised, and the ocean cleared it with room to spare. Put the two pieces together, and the anomaly of timing comes into focus. The ocean is at a record. It reached that record in the wrong season, when it should be cooling, and it did so by opening the widest gap above its own recent normal that the entire year had seen. This is not a system nudging gently against its ceiling. This is a system pressing hard against the ceiling at the exact time of year when it should have the least energy to do so. It is worth being precise about how far this overshoot really reaches, because the phrase out of season can sound vague. The ocean's seasonal cycle is one of the most reliable signals in all of climate science. Year after year, the global average traces nearly the same curve, up through the southern summer to a March and April peak, then down through the middle of the year. That curve is so dependable that you could set your calendar by it. For a late August reading to not merely rise against that curve, but to punch clean through the all-time high, the departure from normal has to be large enough to erase 5 months of expected cooling and then keep going. It is the ocean refusing to follow the one pattern it almost never breaks. The 0.67 degree anomaly is how we put a hard number on that refusal, and the reason a scientist treats an anomaly as more meaningful than a raw temperature is that the anomaly strips out the season. It answers a cleaner question. Not how warm is the ocean today, which depends on the month, but how far from its own normal is the ocean today, which does not. By that measure, the sea in late August was further above its expectations than at any earlier point in the year, including the spring months when the raw temperature was actually higher. So even though the ocean is not at its yearly peak temperature right now, it is at its yearly peak strangeness. It is doing the most unusual thing it has done all year, precisely when it should be at its calmest. Keep the reference period in view as well, because it quietly doubles the weight of the number. Measuring against 1991 to 2020 means the yardstick itself already includes 3 decades of a warming world. A cooler baseline drawn from, say, the middle of the 20th century would make today's anomaly look even more extreme. The fact that the ocean can run this far above a baseline that is itself already warm tells you that whatever is happening now is not just more of the same slow drift. Something is adding a fresh push on top of the trend the baseline already contains, and that push has a name, a location, and a direction. Which forces the obvious question. If the calendar says the ocean should be cooling, what is supplying the heat to push it the other way, all the way to a record? What is strong enough right now to override the planet's own seasonal rhythm? The answer is sitting in the middle of the largest ocean on Earth. To find it, we have to leave the global picture behind for a moment and go to one specific stretch of water in the Pacific, because something has been building there, and it is only just getting started. Part 4. The Pacific starts to turn. There is a stretch of ocean along the equator in the central and eastern Pacific that does not look like much on a map, but it functions like a thermostat for the entire planet. When that patch of water warms up beyond its normal state, the whole world feels it. Weather patterns shift on continents thousands of miles away. Droughts appear in one place and floods in another. Fisheries collapse and recover. And the global average temperature of the ocean, the very number we have been talking about, gets a push upward. That warming of the equatorial Pacific has a name you've heard your whole life, usually in the context of a strange winter or a bad storm season. It is called El Nino. To understand what El Nino is, Picture the Pacific in its normal state. Along the equator, the trade winds blow steadily from east to west, from the coast of South America toward Asia. Those winds drag the warm surface water along with them, piling it up on the western side of the ocean, over near Indonesia and the western Pacific. As that warm water gets pushed west, it leaves the room behind it, and cold water from the deep ocean rises up along the coast of South America to fill the gap. This upwelling of cold, deep water is why the eastern Pacific is normally cool and why the waters off places like Peru are some of the most productive fishing grounds on Earth. The cold water is rich in nutrients, and the fish thrive on it. El Nino is what happens when that whole arrangement breaks down. Every few years the trade winds weaken, sometimes they even reverse, and when they slacken, the warm water that was piled up in the west comes sloshing back east, spreading across the middle of the Pacific like a blanket. The cold upwelling along South America shuts down, smothered by the returning warmth, and suddenly a vast region of the ocean that is normally cool is instead running warm. That is an El Nino. It is not a storm or an event that happens in a day. It is a large-scale rearrangement of heat across the biggest ocean on the planet, and it unfolds over months. Now, why does a warm patch in the Pacific move the global number so much? Go back to what we learned about averages. For the global sea surface temperature to climb, warmth cannot be local. It has to be widespread. And the equatorial Pacific is the single largest, most influential piece of warm ocean real estate in the world. When El Nino spreads warm water across that enormous equatorial band, it is not warming a small sea. It is warming a swath of the planet's surface so large that it drags the global average up all by itself. The Pacific is where the ocean has the most leverage on the whole Earth, and El Nino is the lever being pulled. Scientists watch this region so closely that they have carved it into named zones and track the temperature of each one. The most important of these, the one that has become shorthand for the strength of an El Nino, sits in the central Pacific, and it is called the Nino 3.4 region. It is a rectangle of ocean straddling the equator, and its temperature, compared to normal, is the single most watched El Nino number in the world. When forecasters want to know how strong an El Nino is, they look at the anomaly in Nino 3.4. A reading near zero means neutral conditions, neither El Nino nor its cold counterpart. A positive reading means the water there is warmer than normal, and the size of that positive number tells you how big the El Nino is. As a rough guide, once that anomaly climbs to around 1/2 of a degree above normal and stays there, forecasters say an El Nino has arrived. Push it up toward 1 degree and you have a moderate event. Reach 1.5 degrees and it is strong, and when the number climbs past roughly 2 degrees above normal, you are into the territory that scientists reserve for the rare, powerful events, the ones that reshape a global year. Those are the ones sometimes called very strong, or in casual language, a super El Nino. They come along only a handful of times in a generation, and when they do, they leave their fingerprints on everything from harvest to hurricane seasons to the temperature of the entire planet, so keep that scale in your head. 1/2 of a degree to arrive, 1.5 to be strong, 2 and above for the rare monsters. That is the ruler we are about to measure the current El Nino against. Because what is happening in the Pacific right now is not a modest, run-of-the-mill warming. When forecasters looked at the Nino 3.4 region in the middle of August of 2026, the number they saw was not near the threshold, and it was not near the line for a strong event. It was well past both, and it was still rising. It is worth knowing where the name itself comes from, because it carries the fingerprint of the very fishery this warming disrupts. Generations ago, fishermen along the coast of Peru noticed that every few years, usually around the end of December, the cold, fish-rich waters they depended on would turn unusually warm, and the catch would collapse. Because the warming tended to arrive around Christmas, they called it El Nino, a reference to the Christ child. What those fishermen were witnessing, without the science to name it, was the local face of a planet-scale event. The warm water smothering their coast was the eastern edge of that vast rearrangement of Pacific heat, and the failed catch was the upwelling of cold, nutrient-rich water shutting down. The name has stuck for more than a century, a small piece of coastal folk knowledge that turned out to describe one of the most powerful climate signals on Earth. And powerful is the right word because among all the natural swings the climate makes from one year to the next, El Nino and its cold counterpart are the largest. Nothing else moves the global picture year to year the way the Pacific does when it shifts between these states. It is a coupled event, meaning the ocean and the atmosphere move together, each reinforcing the other. The weakening winds let the water warm, and the warming water further weakens the winds, so the whole system tips into its new state and locks there for months. That coupling is why an El Niño, once it takes hold, is so persistent and so consequential. It is not a passing weather pattern. It is the ocean and the sky agreeing to reorganize themselves across the largest single feature on the surface of the planet, and that is the piece that turns this from a weather story into something heavier. The warm patch in the Pacific that helped push the global ocean to a record is not at its full size yet. The lever is still being pulled. To see just how far, we have to look at the actual number and at what the forecasters expect it to do over the months ahead. Part 5. A very strong El Niño, still climbing. In the middle of August of 2026, the weekly reading for the Nino 3.4 region in the Central Pacific reached plus 2.7 degrees Celsius above normal. Sit with that against the scale we just built. Arrival is around half a degree. Strong is 1.5. The line for the rare, powerful events is roughly 2. And this reading came in at 2.7, comfortably past the threshold for a very strong event, with the peak of the season still months away. That last part is what forecasters kept underlining. This is not an El Niño that has crested and is holding steady near its top. It is an El Niño that is still building. The reading of 2.7 was not a ceiling. It was a waypoint on the way up, and the forecasts for where it goes next are frankly striking. The agencies that specialize in this put the odds of a very strong El Niño developing through the Northern Hemisphere fall and winter of 2026 and into 2027 at greater than 90%. That is an unusually confident forecast in a field that lives and breathes uncertainty. When scientists who study a chaotic system like the ocean and atmosphere put 90% odds on an outcome, they are telling you the signal is loud and consistent. This is not a maybe. This is a system that has already committed to its path, and the forecasters can see where it is heading. To understand how they reach a number like that, it helps to know how these forecasts are built. Rather than run a single prediction, scientists run what is called an ensemble. They take their computer model of the ocean and atmosphere and run it many times over. Each run started with slightly different conditions to account for the fact that we can never measure the present state of the planet perfectly. If those many runs scatter in all directions, the forecast is uncertain. If they cluster together and tell the same story, the forecast is confident. In the August experimental predictions for this El Niño, the ensemble did something that gets a scientist's attention. Every single one of the runs, all 30 of them, produced a peak El Niño strong enough to compete with the most powerful events in the entire historical record. Not most of the runs, not the average of the runs, all 30 unanimously pointing at a monster. When every member of an ensemble agrees that you are heading toward one of the strongest events ever recorded, that agreement is itself the warning. It means there is no plausible version of the near future the models can find where this El Niño fizzles into something ordinary. The disagreement among the runs is only about exactly how extreme it gets, not about whether it gets extreme. There is a reason a reading of 2.7 degrees carries so much more meaning than the raw number might suggest, and it comes back to leverage. The Central Pacific region where that anomaly is measured sits right on the equator, across a stretch of ocean that has an outsized grip on the global climate. When that specific patch runs nearly 3 degrees above its normal, it is not a local curiosity. It is the throttle of the whole system being pushed forward. The atmosphere responds to the warmth there by rearranging its circulation, shifting where rain falls and where drought sets in across entire continents, and by allowing still more of the ocean's stored heat to surface. A number that reaches 2.7 in that region is telling you the engine is not idling. It is running hard and the gauge is still climbing. It also matters that this is not arriving in isolation, but on the heels of years of exceptional ocean warmth, which changes what a reading like this can do. An El Niño of a given strength has a bigger absolute effect when it lands on an ocean already primed with heat, because it does not have to warm the water from a cool start. It only has to add its push to a sea that is already running hot. So the 2.7 degrees in the Central Pacific is not being applied to a rested average ocean. It is being applied to one that entered this event near the top of its historical range. The same throttle setting produces a larger result when the machine is already warm, and this machine was already warm before the throttle moved. The forecasts also point to when this will peak. El Niño events tend to reach their maximum strength in the late fall or winter of the Northern Hemisphere, and this one is expected to follow that pattern, most likely cresting sometime between October of 2026 and January of 2027. And after the peak, there is little sign in the outlook of a quick collapse back to normal. The models keep the El Niño elevated and dominant, with no clear return to neutral conditions before the spring of 2027. In other words, the Pacific is not going to give this heat back quickly. The warm anomaly that helped set an August record is forecast to grow through the winter and linger into the following year. Now put that beside the record we started with. The global ocean hit its all-time high in late August, and it did so while this El Niño was still climbing toward its peak. The Pacific engine that helped push the world's water to a record was, at the moment of the record, running well short of full throttle. If the forecasts hold, and the ensemble is unusually sure that they will, the strongest push from the Pacific is still ahead, arriving in the depth of winter. Which raises a question that is hard to shake once you have asked it. If the ocean can set a record now, on a rising El Niño that has not peaked, what happens to that record when the Pacific reaches full strength this winter? To appreciate how rare the very strong events are, it helps to know that in the entire span of good modern records, only a small handful of El Niño events have reached this class. They are not annual visitors, or even reliably once a decade. They are the exceptions, the events that people who study the climate remember by their years, because each one left a mark on the global temperature record and on the ecosystems it touched. To have the forecasters placing the current event in that category, with the peak still months out, is to be told that we are heading toward one of the rare ones, the kind that reorders a global year. The confidence of the outlook is its own kind of signal, and it is worth dwelling on why. Forecasting the ocean and atmosphere is a discipline built around uncertainty, where honest scientists hedge almost everything, because the system is chaotic and the future genuinely branches. So when the outlook does not hedge, when it puts the odds above 90% and keeps the event elevated and dominant with no clear return to neutral before the spring of 2027, that lack of hedging is information. It means the models are not seeing a fork in the road. They are seeing a single path, already chosen, with the only real question being how far down the ocean travels. In a field that lives on maybe, a forecast this committed is the system telling you it has already made up its mind. But here is where we have to be careful and precise, because it would be easy to walk away thinking El Niño is the whole story. It is not. El Niño is real, it is powerful, and it is doing exactly what we have described. But it is only half of what pushed the ocean over the line. El Niño is the pulse. Underneath it there is something slower and heavier, a foundation that has been rising for decades, and without that foundation, an El Niño this strong would not be landing a record at all. To understand the line the Pacific just crossed, we have to look at what is underneath the spike. Part 6. The baseline beneath the spike. Imagine the tide coming in on a beach where the sand slopes gently upward. Each wave rushes up, reaches a high point and slides back. If you watched a single wave, you might think the water level was set by that wave alone. But the tide is rising underneath all of them. So each successive wave reaches a little higher than the last, not because the waves are getting bigger, but because the whole ocean beneath them is climbing. Eventually, a perfectly ordinary wave washes over a line on the beach that no wave reached an hour earlier, and it does so not on its own strength, but because it is riding on a higher base. That is the relationship between El Niño and the warming ocean, and it is the single most important idea in this entire story. El Niño is the wave. The decades of human-driven warming are the rising tide. When Samantha Burgess of the European Climate Service described this record, that is exactly the picture she painted. El Niño, she said, is adding heat to the system, but it is doing so on top of decades of human-driven warming. The El Niño is the wave rushing up the sand. The warming is the tide that has quietly lifted the whole beach. Let us take the tide seriously, because it is the part that is easy to lose behind the drama of the Pacific. Over the past several decades, the planet has been trapping more heat than it releases, and the overwhelming majority of that extra heat, the great bulk of it, has gone into the ocean. The sea has been absorbing it year after year, storing it in the surface layer and mixing much of it down into the deep. Scientists track this as ocean heat content, and it is one of the steadiest and most alarming trends in all of climate science. It does not swing up and down with the seasons or the years the way surface temperature does. It just climbs. The ocean has been getting hotter, at depth, relentlessly, and that accumulated warmth is the tide beneath every wave. This is why the baseline is doing so much of the work in the record we are looking at. An El Niño of a given strength lands on a warmer ocean, then the same El Nino would have landed on decades ago. The strong El Nino events of the past broke records for their time, but their time had a cooler starting point. Today's El Nino is pushing up from a base that is already elevated, so when it adds its pulse of heat, the total clears heights that were simply out of reach before. The record is not evidence that this El Nino is unprecedented in its own right. It is evidence that the floor it is standing on has risen, and that reframes what the record actually tells us. If you only looked at the El Nino, you might reassure yourself that this is a natural cycle, that the warmth will fade when the Pacific flips back to neutral, that we have seen El Nino come and go before. All of that is true, and all of it misses the point. When this El Nino fades, the wave will slide back down the sand, but the tide will not go with it. The baseline the ocean returns to will be higher than the one it climbed from, because the long-term warming does not reverse on the timescale of an El Nino. The next neutral year will be warmer than the last neutral year. The next El Nino, whenever it comes, will start from a higher place still. Each cycle resets on a raised floor. This is also why Burgess called it a signal of an ocean under growing stress rather than simply a hot year. A single record, taken alone, could be dismissed as a quirk of timing or a strong Pacific event. But she was not describing a quirk. She was describing a system whose baseline is moving, so that natural events that used to produce ordinary warmth now produce records, and records that used to be reserved for the peak of the year now show up in the off-season. The stress she is naming is not the El Nino. The El Nino is temporary. The stress is the steady structural rise underneath it that turns each temporary event into a new high water mark. There is a reason scientists keep insisting on this both, and framing rather than picking one cause. If you say it is only El Nino, you predict the warmth will vanish and the problem will resolve itself, and you will be wrong, because the baseline stays. If you say it is only long-term warming and ignore the El Nino, you cannot explain why the record came this year, in this season, rather than some other. The truth is the combination. The record is the El Nino's pulse laid on top of the warming's floor, and it takes both to reach the height we just saw. Remove either one and the ocean does not cross this particular line in this particular week. The scale of the ocean's role as a heat store is hard to overstate, and it is the reason the baseline matters more than the wave. Of all the extra heat that has been trapped on Earth in recent decades, the ocean has taken up the overwhelming share, the great majority of it, far more than the atmosphere and the land and the ice combined. The sea has been the planet's buffer, quietly absorbing energy that would otherwise have gone into the air we breathe and the ground we walk on. That buffering has spared us the full force of the warming so far, but it has done so by loading the ocean itself, and the ocean does not hold that heat neutrally. It carries it, stores it, and expresses it in surface temperatures, in expansion, in the stress on everything that lives in the water. This is also why the reassurance that it is only a cycle falls apart under its own logic. A cycle, by definition, returns to where it started. The Pacific does swing between its warm and cold states, and in that narrow sense it is cyclical. But the thing the cycle swings around is not fixed. The center point, the baseline, is drifting upward year after year as the deep ocean accumulates heat. So the ocean is not oscillating around a stable average, it is oscillating around a rising one. Each warm swing reaches a little higher than the last, and each cold swing bottoms out a little warmer than the one before. Call it a cycle if you like, but it is a cycle riding an escalator, and the escalator only goes one way. So when we say the Pacific crossed a line, we mean it in two senses at once, and now both are in view. The Pacific crossed a temperature line, the all-time high for the global sea surface, and the Pacific is crossing an El Nino line, climbing past the threshold for a very strong event toward a winter peak. Both crossings are riding on the same rising tide. The question that remains is what a record set on the way up, on a rising base, actually implies about the months ahead. To answer it, we have to look hard at the fact that the ocean did not wait for the peak. Part 7. The record broke before the peak. There is a phrase that keeps surfacing when scientists talk about this record, and it is worth stopping on because it contains the whole warning in 4 words. The record broke early, or, put more precisely, it broke before the peak. The global ocean reached its all-time high, while the force pushing it up was still gathering strength. The engine had not reached full power, and the machine already set a record. We have already seen the two halves of that engine. The El Nino in the Pacific is climbing toward a very strong event, still months from its expected winter crest, and the long-term warming has raised the ocean's baseline to a place where a strong Pacific pulse lands a record. Now hold those two facts together and look at the timing. The record did not arrive at the moment of maximum push. It arrived on the way up. The Pacific was still accelerating, the anomaly in the central Pacific still rising toward its forecast peak, and in the middle of that climb the global ocean surface went higher than it has ever gone. This is the opposite of how you might expect a record to behave. Intuitively, you would think a system reaches its extreme at the moment its driver is strongest. The hottest part of the afternoon comes when the sun is highest, not at 10 in the morning. But the ocean set its record in the morning of this El Nino, so to speak, with the sun still climbing toward noon, and that tells you something uncomfortable about where noon might land. If the ocean can reach an all-time high, with the Pacific engine only partway up, the obvious question is what the surface does when that engine reaches the top, which the forecasts place in the heart of winter. Consider what usually happens with El Nino and global temperature. There is a lag built into the system. An El Nino that peaks in the winter tends to push global temperatures to their highest in the months that follow, often bleeding well into the next year. The heat the Pacific releases takes time to spread through the ocean and the atmosphere, so the warmest global conditions frequently arrive after the El Nino itself has crested. If that pattern holds this time, then not only is the ocean's driver still strengthening, but the fullest expression of its effect on global temperature would come later still, stacking the lag on top of the rising El Nino. The record we are looking at now could turn out to be an early step rather than the summit. Forecasters have a specific set of things they will be watching in the weeks ahead to see where this goes, and it is worth knowing what they are, because it turns a vague sense of dread into concrete signposts. They will watch the weekly temperature readings in the central Pacific to see how much higher the anomaly climbs above the 2.7 degrees it had already reached, and how close it presses toward the peak the models project for the winter. They will watch the global sea surface temperature itself to see whether it keeps posting records or eases back off its August high, and they will watch the anomaly, the gap above normal, to see whether it keeps widening past the widest mark of the year or begins to close. Each of these is a dial with a needle already pointing upward. None of these signposts will give a single dramatic moment, and that is part of what makes this kind of story hard to hold on to. There will not be one day when an alarm sounds. Instead, there will be a slow accumulation of weekly readings, each one a little higher than it should be, each one confirming that the drivers are doing what the forecast said they would. That is how a warming ocean announces itself, not with a bang but with a steady drumbeat of numbers that keep landing on the high side, until one of them crosses a line no one thought would be crossed in that season, which is exactly what just happened in August. Then there is the matter of persistence, which we touched on at the very start but which deserves a harder look. This record was not a single spike. The value of 21.1 degrees appeared on the 21st of August and again on the 22nd. 2 consecutive days at the highest global sea surface temperature ever measured. In a noisy system, a lone extreme reading can be a blip, a momentary alignment of measurements that unwinds the next day. But a value that holds across 2 days is not a blip. It is the system settling into a new state, however briefly. The ocean did not touch the record and recoil. It reached it and rested there. And the persistence goes beyond those 2 days, because those 2 days sat at the top of a broader trend that had been building all year. Remember the anomaly, the gap between the ocean's temperature and its normal for the date. On those record days, that gap reached 0.67 degrees above the 1991 to 2020 average, and that was the widest such gap recorded at any point in the whole of 2026 up to then. So the record days were not an isolated pair of strange readings poking up out of an otherwise ordinary year. They were the crest of a year in which the ocean had been running progressively further above its own normal. The gap had been opening, and on the record days it opened widest. That combination, an early record, a 2-day plateau, and the widest anomaly of the year all landing together, is what makes scientists treat this as a signal rather than a curiosity. Any one of those on its own could be softened with a caveat. The margin over the old record is small, you could say. Or records get set from time to time, that is what records do. But it is the stacking that removes the comfort. The ocean set an all-time high, held it for 2 days, opened its widest gap above normal of the year, and did all of it before the Pacific engine driving it had peaked. Each fact reinforces the others, and together they point the same direction. Look more closely at the lag, because it is one of the most reliable features of how El Nino works, and it deepens the concern. When the Pacific releases its heat during a strong event, that heat does not register fully in the global temperature the same week. It takes time to spread through the ocean surface and into the atmosphere, so the warmest global conditions tend to trail the El Niño's own peak by months. The hottest stretch often lands in the year after the event crests, so we are looking at a situation where the driver is still strengthening toward a winter peak, and the fullest expression of that driver in the global temperature would arrive later still after the peak, bleeding into the following year. The record now is early on 2 counts at once, ahead of the El Niño's peak and ahead of the lagged response that peak will eventually produce. That is why the phrase "a floor, not a ceiling" is the honest way to describe this record rather than a dramatic one. A ceiling is the highest a thing can go. A floor is the lowest it will now sit. When a system reaches an all-time high, while its driver is still building, the reasonable reading is not that it has topped out, but that it has established a new minimum for what is coming. The forecasters will be watching the weekly readings in the Central Pacific climb toward their crest, watching the global surface temperature respond with its built-in delay, and watching whether the anomaly that opened its widest gap of the year in August keeps widening. Every one of those things is pointed upward. The record is where this began, not where it ends. So what does a record set before the peak actually imply? It does not guarantee that an even higher record is coming this winter. The ocean is a complicated system, and forecasts are not certainties. But it strongly loads the dice. When your driver is still strengthening and your system is already at an all-time high, the reasonable expectation is not that things settle back down. It is that the pressure keeps building. The honest reading of an early record is that it is a floor for what is coming, not a ceiling on what has been. And that is precisely the kind of reading that keeps the people who watch this ocean up at night. Part 8. The Anomaly of Timing. We keep circling back to the timing, and that is deliberate, because the timing is the heart of the whole thing. It is easy to hear all-time record and file it away as one more entry in a long list of records that seem to fall every year now. But this record is not interesting because it is slightly higher than the last one. It is interesting because of when it happened, and the when is genuinely anomalous in a way that a raw temperature never fully captures. Go back to the ocean's yearly rhythm and let us make it concrete. The global sea surface temperature traces a curve every year that looks almost the same from one year to the next. It rises through the southern hemisphere summer to a peak in March and April, because the southern hemisphere holds most of the world's ocean, and then it declines through the middle of the year as the southern hemisphere moves into its winter. By August, the curve is well down its back slope. The raw global temperature in August is normally lower than it was in the spring, sometimes by a noticeable margin. August is a cooling month for the global ocean. That is the baseline expectation, and it is one of the most dependable signals in climate science. Now overlay the record on that curve. For the global ocean to set an all-time high in late August, it has to be running so far above its own August normal that it does not merely rise for the season, it leaps past the springtime peak from a previous year. It has to overshoot 5 months of expected cooling and then keep going, past a record that was itself set at the natural high point of the calendar. Picture the seasonal curve as a hill the ocean climbs and descends each year. The old record sat near the top of the hill in March. This new record was set partway down the far side of the hill in August, and yet it stands taller than the summit. The only way that happens is if the entire hill has been lifted underneath the ocean's feet, and lifted by a lot. This is why scientists lean so hard on the anomaly rather than the raw number. The anomaly strips the season out of the picture. It does not ask how warm the ocean is today, which will always depend on the month. It asks how far from normal the ocean is today, which is a fair comparison across any month. And by that measure, the late August ocean was further from normal than at any earlier point in the year. So even though the raw temperature in August is not the highest the ocean reaches in a typical year, the departure from expectation was the highest of the year. The ocean was at its most abnormal precisely when it should have been at its most ordinary. It is easy to hear the word overshoot and picture something small, a modest bump above the expected line. It is not small. To set an all-time record in the cooling half of the year, the ocean has to be running so far above its August normal that it clears a mark set at the natural peak of a different year, 5 months further along the seasonal climb. The distance it has to make up is the entire downhill slope of the seasonal curve plus a little more, and it made it up. That is the scale of the departure hiding inside a gentle-sounding phrase. The ocean did not edge slightly above where it should be. it leapt across months of expected cooling and landed higher than it has ever been. And because the departure is measured against a baseline that already contains decades of warming, the leap is even more striking than it first appears. The ocean is not clearing a low bar left over from a cooler world. It is clearing a bar that was already raised by everything that has warmed the sea in recent decades, and clearing it in the season least likely to allow it. When a system breaks its own most dependable rhythm by that margin, against that already elevated reference, the honest conclusion is not that the ocean got a little warm this August. It is that the forces acting on it right now are strong enough to override the planet's own seasonal machinery, which is not something a small push can do. There is a subtle point here that is worth making explicit, because it changes how you weigh the record. Two different records can have very different meanings depending on how much help they got from the calendar. The March 2024 record was set at the moment of the year most primed to produce a record, riding the seasonal peak. It had the calendar's full assistance. This August record had none. It was set against the calendar in the teeth of the seasonal decline. A record set with help and a record set against resistance are not equivalent, even if the numbers are nearly the same. The one set against resistance is telling you the underlying push is stronger, because it had to overcome the season to get there. And that pushes us toward a question about the near future that is difficult to set aside. The ocean's seasonal curve will keep turning. As the calendar moves toward the end of the year and into the next, the southern hemisphere heads back toward its summer, and the global ocean's seasonal curve begins climbing again toward its natural March and April peak. The El Nino, meanwhile, is forecast to reach its maximum strength across that same winter stretch. So the ocean's seasonal upswing and the El Nino's peak are timed to arrive together. The record we just saw was set on the downslope, against the season, with the El Nino still climbing. What happens when the upslope of the season and the peak of the El Nino line up at the same time? Consider just how dependable the seasonal cycle is, because it is what makes the August record so jarring. The rise and fall of the global ocean temperature through the year is one of the most repeatable signals in all of climate science, tracing nearly the same path year after year, with a regularity you could nearly set a calendar by. The reason is simple geography. The southern hemisphere holds the great majority of the world's ocean, so the global average follows the southern seasons, warming to a peak in March and April after the southern summer, and cooling through the middle of the year. For a system that reliable to be broken, not bent but broken, with an all-time high posted in the cooling half of the year, the force doing the breaking has to be substantial, and it has to be sustained. Now look at how the calendar and the El Nino are about to line up, because it is the alignment that should hold your attention. As the year turns toward its end and into the next, the southern hemisphere heads back towards summer, and the ocean's seasonal curve begins its climb again toward the natural March and April peak. Across that very same stretch, the El Nino is forecast to reach its maximum strength. So the seasonal upswing and the El Nino crest are timed to arrive together. Two forces that were working against each other in August now pulling in the same direction. In August, the ocean set a record while fighting the season. This winter, it may be setting records with the season's help and a stronger engine behind it. The ingredients are not just present, they are converging. No one can say the exact number that will result, and it would be irresponsible to pretend otherwise. But the direction is not really in doubt. Every ingredient that produced the August record is set to strengthen, not weaken, over the months ahead. The seasonal curve turns favourable. The El Nino intensifies toward its crest. The long-term baseline does not drop. When the thing that already produced a record has all of its drivers pointing upward at once, the prudent expectation is more, not less. That is what makes the timing of this record so much more than a footnote. It is not just that the ocean broke a record in the wrong month. It is that the wrong month is about to become the right month, with a stronger engine behind it. Part 9. When the sea runs a fever. So far we have talked about the ocean's temperature as a number, a global average, a line on a chart. But a warm ocean is not an abstraction to the life that lives in it, and it is not an abstraction to the weather that draws on it. When the sea runs a fever, things happen, and the first of those things is a phenomenon that has become one of the defining features of a warming ocean. It is called a marine heat wave. A marine heat wave is exactly what it sounds like, but its consequences are easy to underestimate because they unfold underwater, out of sight. On land, a heat wave is a stretch of days when the air is far hotter than normal, and everyone feels it. A marine heat wave is the same idea applied to the sea, a prolonged period during which the water in a region runs far above its normal temperature for that time of year. It is not measured by a single hot day, but by persistence, water that stays abnormally warm for weeks or months at a time. And where a land heatwave sends people indoors and stresses the power grid, a marine heatwave reaches into an entire ecosystem because the creatures living in that water cannot escape it. They cannot move indoors, they cannot turn on a fan, they are simply held in water that is hotter than what their bodies are built for, day after day, until something gives. It is worth being clear about the difference between the global average and the local reality, because that gap is where the harm lives. The record we opened with, 21.1 degrees, is a planet-wide average, smoothed across every ocean. No creature lives in the global average. A fish, a coral, a bed of shellfish lives in one specific patch of water, and what matters to it is the temperature of that patch. A marine heatwave is a local event, and it can push a particular stretch of sea several degrees above its own normal, even as the global figure moves only a little. So the same warming that nudges the global average to a record can, in specific regions, produce local heat far beyond anything the global number suggests. The average is the headline. The local extremes are where the damage is done. This is why a rising global baseline is so dangerous for ocean life, even when the global increase sounds modest. A warmer baseline means that every regional marine heatwave now starts from a higher floor, so the peaks it reaches climb into territory the local ecosystem has never had to survive. Heat that would once have been a rare, survivable event becomes a frequent, lethal one. The global average creeping upward is not just a statistic, it is the reason that heat waves in the water are arriving more often, lasting longer, and reaching temperatures that push living systems past limits they evolved over long ages to depend on. Here is where the current situation turns from a temperature record into a forecast of harm. As this El Nino ramps up through the coming months, the outlook is for marine heat waves to develop across large stretches of the world's oceans, and the scale being discussed is not modest. Forecasts point to damaging marine heat potentially spreading across close to half of the entire global ocean by the end of 2026. Let that number settle. Not half of one sea, not half of one coastline. Close to half of all the ocean on the planet running hot enough to do biological damage within a single year. The map of where this heat is expected to land is coming into focus as well. The coasts of California and Mexico are flagged as having a very high likelihood of strong marine heat waves, the same eastern Pacific waters that El Nino warms most directly. The Indian Ocean is in line for damaging heat. Parts of the Southern Ocean, down toward Antarctica, are expected to see it too. And this is not purely a future projection. Marine heat waves were already forming off the Pacific coasts of North, Central, and South America earlier in 2026, before the El Nino even reached its current strength. The pattern was setting up before the peak, just as the global record did. The heat is arriving early in these regions, and the forecast is for it to broaden and intensify. Why does a marine heat wave do so much damage? Because ocean life, far more than land life, is tuned to a narrow band of temperature. Many marine species have evolved over long stretches of time in water that stays within a fairly stable range, and their bodies run on that stability. Their metabolisms, their oxygen needs, their breeding cycles, all of it is calibrated to a temperature that does not swing wildly. When the water heats up and stays hot, that calibration breaks. Warmer water holds less dissolved oxygen, so the animals in it are asked to breathe harder in water that offers less to breathe. Their metabolisms speed up, demanding more energy at the very moment the environment is becoming more hostile. For creatures that cannot leave, a marine heat wave is a slow, inescapable physiological squeeze. Some species can respond by moving, and that itself is a form of disruption. Fish that can swim will often head for cooler water, shifting away from the warm regions toward the poles or into deeper, colder layers. That sounds like a solution, and for the individual fish it may be. But it scrambles entire ecosystems and the human systems built on top of them. A fishery that has existed in one place for generations can empty out as the fish. It depends on relocate. Predators lose their prey. Food webs that took a long time to assemble come apart as their pieces move at different speeds and in different directions. The ocean does not simply get warmer, it gets rearranged. We have watched large marine heat waves before, and one of the most studied offers a preview of what widespread ocean heat does. About a decade ago, an enormous patch of abnormally warm water settled over the northeastern Pacific and lingered for years, so large and so persistent that scientists gave it a nickname and tracked it, like a weather system in its own right. It reshaped the ecosystem beneath it. Species shifted out of their usual ranges, some marine life died off in large numbers, harmful algal blooms flared, and fisheries were disrupted up and down the coast. That was one marine heatwave in one region. The current forecast is for damaging marine heat to spread across close to half of the entire global ocean by the end of the year. Multiply the damage of that single warm patch across a large fraction of the world's seas, and you begin to see why the outlook has scientists concerned. What makes these events so destructive is their duration, not their peak. A single hot day means little to the ocean. A marine heatwave is defined by persistence, by water that stays far above normal for weeks and months on end, and it is the length of the exposure that does the killing. Living things can often tolerate a brief spike. What they cannot tolerate is heat that never lets up, that holds through what should be the cool season, that gives them no window to recover. That is precisely the kind of prolonged, unrelenting warmth that a strong El Nino on a raised baseline produces. The heat does not just get higher, it stays longer, and the staying is what breaks the systems caught inside it. And the creatures that cannot move at all are the ones in the most danger. Anything anchored to the seafloor, anything that lives its life fixed in place, has no escape from a marine heatwave. It can only endure the heat or die in it. That includes some of the most important and most vulnerable ecosystems in the entire ocean, the ones that build the living structures other species depend on. To understand what is truly at stake when close to half the ocean runs a fever, we have to look at the ecosystems that cannot flee, starting with the ones that have already been pushed to the edge again and again in recent years. We have to look at the reefs. Part 10. The reefs on the edge. Coral reefs cover a tiny fraction of the ocean floor, less than 1% of it, and yet they shelter a quarter of all the species in the sea. They are the cities of the ocean, dense, crowded, staggeringly diverse places where an enormous share of marine life is born, feeds, hides, and breeds. And they are built by animals that live permanently anchored to one spot, which means that when the water around them turns hot, they have nowhere to go. Of all the ecosystems threatened by a feverish ocean, the reefs are the ones most exposed, and they are already exhausted from the beatings of recent years. To understand why warm water is so dangerous to coral, you have to understand the strange partnership that a reef is built on. Coral animals live in a tight relationship with microscopic algae that reside inside their tissues. The algae capture sunlight and turn it into food, sharing that food with the coral, and in return the coral gives the algae a protected home. That partnership is what gives coral its colour and, more importantly, most of its energy. It is the engine of the whole reef, but it is also fragile, and it is exquisitely sensitive to temperature. When the water gets too warm and stays that way, the relationship breaks down. The coral expels the algae living inside it, and without them it loses both its colour and its main source of food. The coral turns ghostly white. This is what people mean by coral bleaching. The reef has not died at the moment it bleaches, but it has been pushed into a starving, weakened state, and if the heat persists, death follows. Bleaching is not a rare emergency anymore. It has become a recurring catastrophe, striking reefs around the world with increasing frequency as the ocean has warmed. The most severe episodes are called global bleaching events, when heat stress hits reefs across multiple ocean basins at once, and they used to be almost unheard of. Now they arrive with grim regularity. The world has already lived through 4 of these global bleaching events, and the most recent one was so widespread and so damaging that it stands as one of the worst on record. That 4th event only recently came to an end, and here is the part that turns this El Nino from a concern into an alarm for reef scientists. Barely a year after the 4th global bleaching event ended, they are already openly discussing the possibility of a 5th. That is a stunning compression of time. Global bleaching events were once separated by many years. Now the ocean has warmed to the point where reef scientists are watching for the next one before the last one has even faded from memory. The heat forecast for this El Nino, layered on the warming baseline, is exactly the kind of stress that triggers these events, and the regions being flagged are the ones with the most to lose. The map of concern reads like a roll call of the world's most important reef systems. The Pacific, where El Nino warms the water most directly. The Caribbean, with its reefs already battered by repeated bleaching. And Florida's coral reef, the only living barrier reef in the continental United States, which has already endured extraordinary heat in recent years, water so hot in some shallow areas that it shocked the scientists monitoring it. These are not remote, abstract places. They are reefs that people fish on, dive on, and depend on for the protection they give to coastlines by breaking up storm waves before they reach the shore. When a reef bleaches and dies, a coastline loses a wall it did not know it was relying on. The acceleration of these events is the part that has changed most, and it is worth measuring it against how things used to be. For a long stretch of the modern record, global bleaching events were genuinely rare, separated by many years, rare enough that each one was a shock. The ocean would warm, the reefs would suffer, and then there would be a long gap before the next one, a gap long enough for the reefs to begin rebuilding. That spacing is gone. The world has now moved through 4 of these global events, and the most recent was among the most severe and widespread ever documented. To be discussing a 5th barely a year after the 4th ended is to watch the gaps between catastrophes collapse toward nothing. That collapse of the recovery interval is, in a sense, the whole danger stated in a single trend. Reefs are not fragile in the ordinary sense. They are ancient, resilient systems that have survived enormous changes over their long history, and a bleached reef is not necessarily a dead one. Given cooler water and time, coral can take its algae back and slowly heal. The threat is not that heat is possible. The threat is that heat is becoming constant, arriving again before the healing from the last event is anywhere near complete. A system built to recover across years is being handed only months, and no amount of resilience can outrun a clock that never resets. What makes a 5th bleaching event so serious is that reefs need time to recover, and time is exactly what the warming ocean is taking away. A reef that bleaches can, under the right conditions, regain its algae and slowly rebuild. But that recovery takes years of cooler, calmer water. If bleaching events come one after another, separated by too little time, the reefs never get the breathing room they need. Each event hits a system already weakened by the last one. The recovery windows shrink until they close entirely, and what was once a resilient ecosystem that could bounce back becomes one grinding down toward collapse. The danger is not any single bleaching event. It is the rhythm of them arriving faster than the reefs can heal. Florida offers a preview of how extreme this local heat can get, and it is a recent and sobering one. In the shallow waters around the Florida Keys during a recent summer, sea temperatures climbed to levels that genuinely shocked the scientists monitoring them, in some spots reaching readings more like a warm bath than open sea. Reefs there bleached severely, and in places the coral died before it could even bleach, cooked in place by water that stayed too hot for too long. Restoration teams scrambled to pull young corals out of the water entirely, moving them to tanks on land to keep them alive. That is what the leading edge of ocean heat looks like when it reaches a reef, and it happened before the current El Nino had spun up to its present strength. The stakes extend well beyond the reefs themselves, because a reef is not only a wonder to look at, it is working infrastructure. Reefs break up incoming storm waves before they reach the shore, shielding coastlines from erosion and flooding, a service worth an enormous amount to the communities behind them. They shelter the young of countless fish species that fisheries later depend on, making them nurseries for a large share of the catch that feeds coastal populations. When a reef bleaches and dies, all of that goes with it. The wave barrier, the nursery, the tourism, the food. So the compression of bleaching events into a rhythm faster than the reefs can heal is not only an ecological tragedy, it is the loss of a piece of coastal defense and food security that took thousands of years to build and cannot be quickly replaced. So when we look at the global ocean record and the strengthening El Nino behind it, the reefs are where the number becomes flesh. 21.1 degrees is a global average, but for a reef in the Caribbean or off Florida or across the Pacific, the relevant temperature is the local one, and a strong El Nino on a warm baseline is precisely the recipe for pushing that local water past the bleaching threshold. The reefs are the early warning system of the warming ocean, the place where the stress shows up first and most visibly, and right now, barely recovered from the last blow, they are being lined up for another. But the reefs are not the only living system being pushed toward its limit. There is another, one that reaches directly into the lives and livelihoods of people, and it is being described in language that could not be more stark. Part 11. The Fisheries Breaking Point. There is a phrase that keeps coming up when scientists describe what a strong El Nino does to the world's fisheries, and it is the phrase that gives this whole story its edge. Breaking point. The marine heat waves that a strong El Nino brings could push many sensitive fisheries to a breaking point. Not stress them, not reduce them, push them to the point where something snaps. And unlike the reefs, which most people will never see, the fisheries are where a warming ocean reaches directly into human life, into food supplies, into economies, into the survival of coastal communities that have fished the same waters for generations. To see why fisheries are so vulnerable, start with the fish themselves, and with the fact that a warming ocean does not simply thin them out. It moves them. Fish are exquisitely sensitive to water temperature, and when their waters heat up, many of them do the only thing they can. They relocate following the temperature they are built for toward cooler seas, toward the poles, or down into deeper, colder layers. The pelagic species, the ones that roam the open ocean, are especially mobile. Tuna, sardines, mackerel, these are fish that can and do shift their migration routes when the water warms, abandoning the places they have reliably occupied and showing up somewhere else, or at some other depth, or at some other time of year. For the fish, this is adaptation. For the people who depend on them, it is chaos. A fishery is not just a population of fish. It is an entire human system built around the assumption that those fish will be in a particular place at a particular time. Boats, ports, processing plants, markets, jobs, entire local economies are organized around that predictability. When the fish move, the predictability collapses. A fleet that has always found its catch in one stretch of water may sail out to find it empty, the fish having moved beyond reach. A community whose economy runs on a seasonal arrival may find the season scrambled or the arrival gone. The fish may still exist, but they are no longer where the human system was built to catch them, and rebuilding that system around a moving target is slow, expensive, and sometimes impossible. Then there are the creatures that cannot move, and here the damage turns from disruption to death. The species that live on or near the seafloor, the benthic communities, are as trapped as the coral. Mollusks like clams and mussels and oysters, sea urchins, crabs and other crustaceans, all the life that is fixed in place or slow to relocate, has no way to flee a marine heat wave. It simply has to endure the heat, and much of it cannot. The same physiological squeeze that threatens the reefs threatens these animals too. Warmer water holds less oxygen, their metabolisms race, and the habitat that supports them degrades around them. Whole beds of shellfish can die in place during a severe marine heat wave, and the fisheries built on them go down with them. The economic scale of all this is not small, and it is not a future projection. Marine heat waves are already estimated to cost the world billions of dollars every year through lost catches, damaged aquaculture, and the cascading effects on the industries and communities that depend on the sea. Aquaculture, the farming of fish and shellfish, is particularly exposed because it concentrates animals in fixed locations, in pens and beds that cannot be moved when a heatwave rolls in. A marine heatwave can wipe out a season's worth of farmed stock in a matter of weeks, and every one of these losses lands hardest on the coastal communities and developing regions that have the fewest resources to absorb the blow, the places where fishing is not a hobby or an industry, but the difference between getting by and not. Now connect it back to where we started. The record we opened with, 21.1 degrees, is a global average, an abstraction. But the fisheries are where that abstraction turns into empty nets and shuttered docks, and communities watching the sea they have always relied on turn against them. The forecast is for marine heat to spread across close to half the global ocean by the end of the year, with a very strong El Nino still building toward its peak. That is not a recipe for a difficult season. It is a recipe for pushing sensitive fisheries all around the world toward the breaking point that scientists keep naming. The temperature line the Pacific just crossed is, for a great deal of ocean life and a great many people, a line beyond which the systems they depend on begin to fail. The classic example of a fishery collapsing under El Nino is the very one that gave the phenomenon its name, and it is worth understanding because it shows the mechanism cleanly. Off the coast of Peru lies one of the most productive fishing grounds on the planet, built on the cold, nutrient-rich water that normally wells up from the deep along that coast. That upwelling feeds vast schools of small fish, which in turn support one of the largest single-species fisheries in the world. When a strong El Nino arrives, the warm water spreading east shuts that upwelling down. The nutrients stop rising, the food chain starves from the bottom and the fish vanish, either dying off or fleeing to cooler water. Entire fishing economies have been thrown into crisis by this exact sequence, repeatedly over the decades. It is the original El Nino disaster, and it is a template for what warm water does to a fishery that depends on cold. Aquaculture faces a version of this danger with even less room to escape, and it is a growing share of how the world feeds itself from the sea. Farmed fish and shellfish are raised in fixed pens and beds, concentrated in one place and unable to be moved when a heatwave rolls in. A marine heatwave can sweep through a farming region and kill a season's worth of stock in a matter of weeks, drowning the animals in warm, oxygen-starved water they cannot leave. And because aquaculture concentrates so much value in fixed locations, the losses can be sudden and enormous. As the world has come to rely more heavily on farmed seafood, it has, without quite meaning to, placed more of its food supply directly in the path of exactly the kind of ocean heat that a strong El Niño brings. And the failures do not stay in the water. A warmer ocean does not only reshape what lives in the sea, it reshapes the sky above it and the storms that form there, because the same heat that stresses the fish is fuel for something else entirely. Part 12. The water that feeds. The storms. Every hurricane, every typhoon, every great rotating storm that has ever threatened a coastline was, at its core, an engine that runs on warm water. That is not a metaphor. It is the physical truth of how these storms work, and it is the reason a record warm ocean is not only a threat to the life within the sea, but a threat that reaches onto land, into the places where people live, through the weather the ocean helps to build. A tropical storm is in essence a machine for converting the heat stored in the ocean's surface into wind. It works like this. Warm ocean water evaporates readily, loading the air above it with water vapor. That warm, moist air rises. As it climbs and cools, the water vapor condenses back into liquid, forming clouds and rain, and in doing so it releases the heat it carried, warming the surrounding air and driving it to rise faster still. That rising air pulls in more warm, moist air from the surface below, which rises in turn, and the cycle feeds on itself. Given the right conditions, this becomes a self-sustaining engine, a storm that draws warmth up out of the ocean and spins it into wind. The warmer the surface water, the more fuel the engine has, and the more powerful the storm it can build. The connection between ocean heat and storm strength is not a loose correlation. It is written into the thermodynamics of how these storms are built. There is an upper limit on how strong a tropical storm can theoretically become in a given environment, and that limit rises as the underlying ocean warms. Warmer surface water raises the ceiling on a storm's potential intensity, giving the strongest storms more room to grow. It does not mean every storm reaches that ceiling, because many other factors can hold a storm back. But it raises the top end of what is possible, and it is the top end, the rare and violent storms, that does the most damage when it comes ashore. There is also the matter of how much water these storms carry, which is often the deadlier threat. A warmer ocean feeds more water vapor into the air above it, and a warmer atmosphere can hold more of that vapor before it falls as rain. So storms forming over a record warm ocean have more moisture available to wring out, which means heavier rainfall and worse flooding when they make landfall. In recent years, some of the most destructive storms have done their damage not primarily through wind, but through staggering quantities of rain, and a hotter ocean is a direct contributor to that shift. The warmth we measured at the surface becomes, downstream, the water that falls on inland towns far from any coast. This is why sea surface temperature is one of the first things forecasters look at when they assess how dangerous a storm season might be or how strong a particular storm could become. There is a rough threshold, a surface temperature above which the ocean has enough warmth to sustain a tropical storm, and the further above that threshold the water runs, the more energy is available. A record warm ocean means a larger fuel tank spread across a wider area, available for longer. It does not by itself create storms, which need other ingredients too, but it raises the ceiling on how strong they can get when they do form. It loads the dice toward intensity. One consequence of warmer surface water that has drawn particular concern in recent years is rapid intensification, the phenomenon where a storm strengthens explosively in a short span of time, sometimes leaping from a modest system to a monster in a single day. Rapid intensification is one of the most dangerous things a storm can do, because it can outpace the warnings, turning a manageable threat into a catastrophe faster than communities can react. And warm ocean water is one of its key ingredients. When a storm passes over water that is exceptionally warm, especially warmth that runs deep rather than sitting in a thin surface layer, it has the fuel to intensify quickly and to keep intensifying. A record warm ocean, with heat stored not just at the surface but mixed down into the layers below, is precisely the kind of environment that makes rapid intensification more likely. There is a further wrinkle worth naming, and it involves the very El Nino we have been tracking. El Nino has complicated effects on tropical storms, and they are not the same everywhere. In some ocean basins, a strong El Nino actually tends to suppress storm activity by changing the winds high in the atmosphere in ways that tear developing storms apart. In others, it can enhance activity. So a strong El Nino does not simply mean more storms everywhere. What it does mean, reliably, is more heat in the ocean available to the storms that do form, and a rearrangement of where the risk is concentrated. The overall energy in the system goes up even as its distribution shifts, and laid on top of the long-term warming of the ocean, which raises the baseline warmth available in basin after basin, the trend in the fuel supply points in one direction. Rapid intensification is the specific danger that warm, deep water makes more likely, and it is worth understanding why depth matters as much as surface heat. A storm churns the ocean beneath it, dragging cooler water up from below, and normally that upwelling of cooler water acts as a brake, starving the storm of fuel as it stirs its own cold water to the surface. But when the warmth runs deep, when the heat is not just a thin skin at the surface, but mixed down through the layers below, that brake fails. The storm churns and finds more warm water underneath, not cooler water, so it keeps drawing fuel and keeps strengthening. A record warm ocean with heat stored well below the surface is precisely the kind of ocean that removes the brake, and removing the brake is how a manageable storm becomes a monster in a single day. The El Nino complicates the geography of this risk in ways worth naming plainly, because a strong event does not simply mean more storms everywhere. In the Atlantic, a strong El Nino tends to increase the high-level winds that tear developing storms apart, which can actually suppress the number of hurricanes that form there. In parts of the Pacific, it can do the opposite, feeding storm activity. So the effect is not uniform. What is uniform is the heat. Wherever storms do manage to form, they are forming over an ocean carrying more energy than it has ever carried, and that raises the ceiling on how strong those storms can become. The distribution of the risk shifts from basin to basin, but the fuel in the tank everywhere has gone up. So the record warm ocean is not a story that ends at the waterline. It is connected through the physics of evaporation and rising air to the storms that come ashore and flood cities and tear apart coastlines. The same warmth that bleaches the reefs and drives the fish toward the poles is the warmth that a hurricane reaches down and pulls up to build itself. When we say the Pacific crossed a line, we are not describing an event sealed away out at sea. We are describing a change in the amount of energy available to the entire climate system, energy that expresses itself as marine heat waves in the water, and, potentially, as more intense storms in the air above it. The ocean and the sky are one connected engine, and we just watched the ocean side of that engine reach a temperature it has never reached before. Part 13. A rising sea you cannot see. There is a consequence of a warming ocean that is quieter than a marine heatwave and slower than a storm, and precisely because it is quiet and slow, it is easy to overlook. It does not announce itself with dead fish or bleached reefs or wind. It works in millimeters, at the edges of the world's coastlines, and it follows almost automatically from the heat we have been discussing. When you warm the ocean, the sea itself rises, and a good part of that rise comes not from melting ice, which most people think of first, but from a simpler piece of physics happening in the water we just watched set a record. The physics is this: when water warms, it expands. Heat it, and each drop takes up a little more space than it did before. This is true of almost everything, but in the ocean it happens on a scale that reshapes the planet. The world's oceans hold an almost incomprehensible volume of water, and when you warm that entire volume, even slightly, the expansion adds up to a meaningful rise in sea level all on its own. Scientists call this thermal expansion, and it has been one of the largest single contributors to the sea level rise the world has already experienced. It is, in a real sense, the sea level signature of the ocean's fever. The same stored heat that shows up as a record surface temperature also shows up, more slowly, as water climbing a little higher against every shore. What makes thermal expansion so relevant to our story is that it responds to exactly the thing we have been tracking, the heat content of the ocean. As the sea absorbs more energy and warms, not just at the surface but through its depths, it expands. The record surface temperature is the visible face of a broader accumulation of heat in the ocean, and that broader accumulation is what drives the water to expand and rise. So the record is connected through this slow physics to a change that will outlast the El Niño entirely. When the Pacific eventually flips back toward neutral and the surface temperature eases off its record, the expansion driven by the deeper accumulated heat does not simply reverse. The heat that has worked its way into the ocean's depth stays there for a long time, and the expansion it causes stays with it. A few millimeters of rise sounds trivial, and in any single year it is nearly imperceptible. No one stands on a beach and watches the sea climb, but sea level rise does its damage not through the average, but through the extremes it amplifies. A coastline sits at a certain height above the water, engineered and settled for the sea as it used to be. Raise the baseline of the ocean even slightly, and every storm surge starts from a higher point. Every high tide reaches a little further inland. Every coastal flood goes a little deeper and lasts a little longer. The rise itself is quiet, but it loads the extremes. It turns floods that used to be rare into floods that happen often, and floods that used to be severe into floods that are catastrophic. A warmer ocean is a higher ocean, and a higher ocean is a more dangerous one at exactly the moments when the sea is already trying to come ashore. It is worth being honest about the timescales here, because they are different from the rest of our story. The marine heat waves and the storm fuel are immediate, playing out over this season and the next. Thermal expansion and sea level rise are patient. They accumulate over years and decades, and the contribution from any single warm year is small. But that patience is exactly why it belongs in this account. The record we are looking at is not only an event that stresses the ocean right now, it is a marker of accumulated heat that will keep pushing the sea upward long after this particular El Niño is a line in the history books. The ocean has a long memory. The heat it takes in this year becomes part of a rise that our coastlines will be reckoning with for a very long time. Thermal expansion has been one of the single largest contributors to the sea level rise the world has already measured, on the same order as the water added by melting ice. That surprises people, because the melting of glaciers and ice sheets gets the attention, and it should. But a large share of the rise recorded so far has come simply from the ocean getting warmer and taking up more room. It is the least visible cause of a very visible problem, a rise driven not by anything pouring into the sea, but by the sea itself swelling as it warms, and it scales directly with the heat we have been tracking. The more energy the ocean absorbs, the more it expands, and the higher it climbs against every shore. The cruelty of it is that this rise is effectively locked in for the long haul, because of how long the ocean holds its heat. The warmth that has worked its way into the deep ocean will stay there for centuries, and the expansion it drives will stay with it. So even in a future where the warming slowed, the sea would keep rising for a long time from the heat already banked, a commitment made by the energy the ocean has already swallowed. The record we are looking at is a marker of that banked heat. It is not only a stress on the ocean today, it is a deposit into a rise that coastlines will be paying interest on for generations in the form of higher tides, deeper storm surges, and floods that reach a little further inland each decade. So the record warm ocean writes itself into the world in more than one timescale at once. In the short term, it is marine heat and storm fuel and stressed ecosystems. In the long term, it is a sea that sits a little higher against every shore, quietly raising the stakes of every future storm. It is the same heat, the same ocean, the same record, expressing itself fast and slow at the same time, and to understand where all of this is heading, it helps to look backward for a moment, to the last time the Pacific spun up an El Niño of this magnitude, because we have stood near this line before, and what happened then is a warning about what may happen now. Part 14, We Have Been Here Before, Almost. The current El Niño is not the first of its kind, and the current ocean record is not the first time the world's seas have climbed to a frightening high. To understand the weight of what is happening now, it helps to look back at the recent past, because the last decade has handed us two clear precedents, and both of them tell us something about the road ahead. We have been near this line before. What is different this time is where we are standing when we reach it. Go back about a decade to the El Niño that peaked across the winter of 2015 and 2016. That was one of the strongest El Niño events ever recorded, a genuine super El Niño, the same category of event that the current forecasts are pointing toward. And its effects were felt around the world. Global temperatures spiked to record highs, with the heat bleeding well into the year that followed, exactly the lag we discussed earlier. And in the ocean, that Super El Nino helped drive one of the most severe coral bleaching episodes the world had ever seen. A global bleaching event that scarred reefs across every tropical ocean basin and killed coral on a massive scale. That is the template. A very strong El Nino arrives, global temperatures leap, and the reefs pay a terrible price. It is the pattern the current El Nino threatens to repeat, and the forecasts placing this event in the same category as 2015 and 2016 are precisely why reef scientists are bracing. But the more recent precedent may be the more revealing one, and it is the reason the current record cannot be waved away as just another El Nino year. Look at what the ocean did across 2023 and 2024. During that stretch, the world's oceans went through a run of record warmth that stunned the scientists watching it. Day after day, month after month, the global sea surface temperature ran at or above previous records, climbing to heights and holding there in ways that surprised even the researchers who study this for a living. The previous record that this August reading just beat, the 21.09 degrees from March of 2024, was set during that very run. That period established just how hot the ocean could get, and it did so recently enough that the water has not meaningfully cooled since. And that is the crucial difference between now and the previous Super El Nino. When the El Nino of 2015 and 2016 arrived, it climbed from a cooler starting point. When the current El Nino is arriving, it is climbing from the elevated plateau left behind by the record warmth of 2023 and 2024. The baseline has moved up in the intervening years, so the same strength of El Nino that broke records a decade ago is now landing on an ocean that was already running near record warmth before the El Nino even began. It is the rising tide again, made concrete by history. Each time we return to this line, we return to it from a higher place than the time before. This is what turns a comparison to the past into a warning about the future. If you only had the 2015 and 2016 precedent, you might expect this El Nino to produce a spike and then a return to something like normal. But the 2023 and 2024 run showed that the ocean's normal has itself shifted upward, and that the warmth can persist far longer and climb far higher than a single El Nino would suggest on its own. Put the two precedents together, and the picture is not a spike on a stable baseline. It is a spike on a baseline that is itself climbing, with each successive event setting off from higher ground. The August record is the newest evidence that the pattern is continuing, and continuing in the direction the science has long expected. There is an even older precedent worth naming, because it set the standard the others are measured against. Near the end of the 20th century, in the winter spanning 1997 and 1998, the Pacific produced a Super El Nino of extraordinary strength, one of the most powerful ever recorded. It drove global temperatures to record highs for its time, unleashed floods and droughts across continents, and battered coral reefs worldwide. For years afterward, it was the benchmark, the event people pointed to when they wanted to describe what a truly strong El Nino could do. The fact that the current forecasts place this event in the same rarefied company as that one, and as the winter of 2015 and 2016, tells you the class of event we are dealing with. These are the ones the history books remember. What genuinely unsettled scientists about the more recent stretch, though, was not any single event but the persistence, the way the ocean simply refused to cool. Across 2023 and 2024, the global sea surface ran at record or near record warmth for month after month, climbing higher and holding longer than the researchers watching it expected, in ways that outran the explanations they had on hand at the time. It was warmth that behaved as though the ocean had shifted to a new setting and stayed there. That is the plateau the current El Nino is climbing from. Not a cool, rested ocean waiting for a push, but a sea that had already been running hot for a sustained stretch and had not come back down before the next strong event arrived to lift it further. So when we say we have been here before, almost, the almost is doing real work. We have seen Super El Nino events. We have seen record ocean warmth. But we have not seen a Super El Nino of this magnitude arriving on top of a baseline lifted this high, this recently, with the event still climbing toward its peak. Every previous version of this line was crossed from lower ground. This one is being crossed from the highest ground yet, and the engine driving it has not finished its climb, which brings us back finally to the line itself, and to what it really means that the Pacific has crossed it now. Part 15. The Line. We just crossed. Let us stand back and see the whole shape of it, because we have covered a great deal of ocean, and the pieces only reveal their full weight when they are placed side by side. On the 22nd of August 2026, the surface of the world's ocean reached 21.1 degrees Celsius, the highest it has ever been measured. It happened in the wrong month, when the ocean should be cooling. It happened before the El Nino driving it had peaked. It held for 2 days, and it opened the widest gap above normal the year had seen. And it happened on a baseline lifted by decades of accumulated heat, with a very strong El Nino still climbing toward a winter crest. That is the line the Pacific just crossed, and every part of it points the same direction. Now, whenever a story like this is told, certain objections rise up, and they deserve an honest answer rather than a dismissal, because some of them contain a grain of truth that is worth handling with care. The most common one goes like this. This is just El Nino. It is a natural cycle, it has happened before, and it will pass. And the honest response is that the first half of that is true, and the second half misses the point. El Nino is natural, and it will pass. But the record is not El Nino alone. It is El Nino laid on top of a warming baseline, and it took both to reach this height. When the El Nino passes, the wave slides back down the sand, but the tide it rode in on stays. The baseline does not reset when the Pacific flips, so yes, this warmth will ease, and no, that does not make it a false alarm because the floor it eased down to will be higher than the floor it climbed from. Calling it just El Nino is like calling a flood just the rain, while ignoring that the river was already running high before the storm. A second objection cuts deeper, and it is the one about the data itself. How do we know the numbers are real, and not the product of adjustments or manipulation? This is a fair thing to ask of any measurement that carries this much weight, and the answer is reassuring in its boringness. The record does not come from a single instrument or a single method that could be quietly tuned. It comes from a blend of independent measurement systems, satellites reading the ocean from orbit, buoys anchored and drifting across the seas, ships logging temperatures as they cross, and robotic floats sampling the water directly. These systems are built and run by different groups. They cross-check against one another, and the same warming shows up across all of them and across multiple independent reconstructions of ocean temperature. The methods are public. The record is not one lab's claim. It is the convergent result of many ways of measuring the same ocean, and they agree. There is a third idea that circulates, stranger than the others, that the ocean is being heated deliberately through some secret program or engineering scheme. It is worth addressing plainly because it dissolves the moment you consider the scale. The amount of energy involved in warming the surface of the entire global ocean is planetary, beyond anything human engineering could deliberately inject into the sea, and beyond any reason to try. There is no mechanism for it and no evidence of it, and there does not need to be, because the warming we observe is fully consistent with physics we have understood for a very long time. The way certain gases in the atmosphere trap heat, combined with the natural way the Pacific redistributes ocean heat during an El Nino. The explanation that requires no secret is the one that fits every observation. The ocean is warming because the planet is trapping more heat, and the Pacific is rearranging that heat right now. That is enough. It is more than enough. It is worth naming plainly what is not being claimed here, because the honest version of this story is stronger than any exaggeration. No one is saying a single record day proves anything on its own that the longer trend had not already shown. No one is saying the exact temperature of next winter can be predicted, or that every consequence we have discussed is certain to arrive at full force. The ocean is a vast and complicated system, and humility about the details is not weakness, it is accuracy. What can be said, with confidence, is narrower and still sobering. The ocean reached a height it has never reached, in a season it should not have, before its driver had peaked, on a baseline that keeps rising. Those are not predictions, they are measurements, and it is the combination of those measurements, not any one of them, that carries the weight. Pull any single thread and it could be softened. The margin over the old record is small, records get broken. One El Nino will pass, but the threads are woven together, and woven together they tell a coherent story that no single caveat unravels. An all-time high, held 2 days, at the widest anomaly of the year, in the cooling season, ahead of the peak, on a climbing baseline. Each fact reinforces the next. That is why the people who watch this ocean are not treating the August record as a curiosity to be explained away, but as a signal to be taken seriously, and why the question it leaves us with is one worth sitting with rather than shrugging off. Strip away the objections and what remains is a single, coherent picture, and it is the picture Samantha Burgess sketched in one sentence when the record came in. An ocean under growing stress. El Nino adding heat, on top of decades of human-driven warming. The record is the visible symptom of a system whose baseline is climbing, so that natural events which once produced ordinary warmth now produce all-time highs, and highs that once belonged to the peak of the year now appear in the off-season. The line the Pacific crossed is a temperature line and an El Niño line at once, and both were crossed while riding on the same rising tide. Here is the thought that lingers, the one that is hard to set down once you have picked it up. Everything that produced this record is set to strengthen. The El Niño is climbing toward a peak that forecasters place in the heart of winter, when the ocean's own seasonal curve will be turning upward again toward its natural high. The baseline is not going to drop. The heat already stored in the deep ocean is not going anywhere soon. Every ingredient that combined to push the sea to a record in the wrong month is timed to intensify and to align over the months ahead. The ocean set its all-time high with the engine only partway up, and the engine is still climbing. Which leaves us with a single question, and it is not rhetorical because the answer is genuinely unknown and will be written into the ocean over the coming months. If the global sea surface could reach an all-time record in late August, against the season, before the El Niño had even peaked, then what number is waiting for us this winter, when the Pacific reaches full strength and the season turns warm again at the very same time?